Now that we have gone through the four fundamental subspaces defined by a matrix, the column space, the null space, the row space, and the left null space, let's try to put these things together and also to review some of the things that we did earlier to see how these things are actually falling in place to form a nice big picture. Let's start with one beautiful picture. This is our favorite matrix, A, m by n matrix, m rows and n columns, and the rank is R. So it's a general matrix. There's no constraints on its shape or rank or anything. And once we have that, we can think of a set of linear equations with some constants, any set of constants, but there will be m of them because m rows, m equations. So we can see that this is a mapping of a vector in Rn in green to a vector in Rm in red. We can also see that the moment you write this equation as a statement of truth, we are saying that B is a linear combination of the columns of A. The moment you find the right coefficients, the weighting factors for the vectors, you have solved the system of linear equations. So that's what it means. Now, from the topology, from the layout of A itself, the numbers therein, we have a column space. Take all possible linear combinations of the columns of A, you get the column space. And how many linearly independent columns are there? That would be the same as the rank of A, which is R. So there is a subspace called the column space within the output space, which is Rm. So on my right hand side, I have Rm. Soon you will see Rn on the left hand side. So there's a subspace, so that means it's got the 0 vector in there. That is what that little circle means. So that's the output side. Then we said on the input side, let's think about all possible vectors such that Ax actually goes to 0. So all the vectors that get transformed to the 0 in the output side, obviously the 0 in the input side will go to the 0 on the output side, but there may be other vectors on the input side that go to the same 0 vector on the output side. Those vectors will form the null space. Oh, by the way, the column space is also called image for obvious reasons. It's the image of something on the input side. But for some mysterious reasons, it's also called the range. And the null space on the input side is also called kernel. Mathematicians are very fond of the word kernel, so you will see it in so many different places with so many different meanings. Another such word is canonical. Canonical. All right. So you have some vectors on the input side going to the 0 vector on the output side. The collection of all such vectors, the set of such vectors, we call that the null space. Then we said there are other vectors on the input side that are not in the null space. They are actually orthogonal complements of the vectors in the null space. Those vectors form a space, and that is called the row space. That is called the co-image, which is like, I guess, the corresponding part of the image on the input side. The thing to understand is that if there is a vector in this green row space, take any such vector, you will get only one vector in the column space. The mapping from the green row space to the red column space is 1-to-1, including the 0 vector, which is a part of our row space also, that will uniquely go to the 0 vector on the output side. We took an example where we said our row space was the xy plane and the null space was the z-axis, orthogonal complements. Then we looked at this R3 and realized that most of the vectors in this R3 are neither on the xy plane nor on the z-axis. They are angled in different ways, in different random directions. All those vectors can be written as a linear combination of the vectors coming from the row space, the green part, and the purple part, the vectors coming from the null space. And they will also go to the same column space. All vectors on the input side will have to go to the column space, obviously, because of this equation, Ax. Ax really means a linear combination of the columns of A, and all such linear combinations will find home in the column space. Now we have accounted for all vectors on the input side. In our R3 example, it was the xy plane, the z-axis, and all possible linear combinations which will span R3, which is the input space. So there is nothing to go to the left null space, which is the blue part. It's also called left kernel or co-kernel. So this is the picture. Rn, the input space, is called the domain. So if you want to fill Rn, you will take the row space vectors and the null space vectors and start forming the linear combinations. In other words, if you find the basis of the row space and the basis of the null space, union them together as a basis set, and that will form a basis for Rn. Similarly, on the output side, the codomain, which is Rm, you can find the basis for the column space and the basis for the null space, put them together, and that will form the full basis of the codomain, and you will see that there are m of them because R is the dimension of this. So R basis vector is there, m minus R for the left null space. So add them up, you get m, and that is the dimension of Rm. All these things are beginning to coordinate very well and form a very nice picture. Now we can talk about the connection between the null space and the row space. Both are subspaces of Rn, and the dimensions add up to n, which is the rank nullity theorem on the input side. The dot product of any vector in the row space with any vector in the null space will be 0. They are orthogonal, and since they span all of Rn, the orthogonal complements too. So take the union of the basis for the row space and the null space. That will give basis for the input space Rn. So all vectors in the null space will go to the 0 vector on the right hand side in Rm. The rest will have to go to non-zero vectors in the right hand side, and that would be the non-zero part of the column space. And then there is this splitting of any vector in the input side, 2 vectors in the row space and vectors in the null space, and A times x perpendicular, the part in the null space, will be 0, and so those things also will end up in the column space. As I kept harping on, most of the vectors in the input side are neither in the row space nor in the null space. So here is another example, a full rank square matrix. What's the rank? Full rank, hello, so 3. It is invertible. What is the column space? It's all of R3. And does AX equal to B have solutions? Every single time, because it is full rank, B has to be in R3. So every single one of them will have unique solutions. What's the row space? It is also all of R3. So when a matrix has the row space the same as the column space, that's when it is actually non-singular. It's invertible. What's a good basis? The identity matrix, because it's all of R3. It's invertible full rank square, and all invertible full rank square matrices have the same row and column spaces. They will row reduce to the identity matrix. They are row equivalent or column equivalent to the identity matrix. And you could use the identity matrix as the basis for the column space or the row space. So full rank, it is a square matrix, n by n, full rank, so R is n. RREF is just identity matrix. Basis for row space and column space would be just the identity matrix. The row space on the left hand side is all of Rn. The column space, red, right hand side, all of Rn. Null space is trivial, just 0 vector. Left null space also is trivial, just a 0 vector. If it is rank deficient, then it gets more complicated, perhaps more interesting. The RREF will have some 0 rows because there are only R pivots. So the first R rows will have something like identity matrix, but shuffled in with the free variable columns, and this symbol represents shuffling in. And then you will have n minus R rows that are 0 rows. So the basis for the row space would be the pivot rows of A or the RREF. The basis for the column space will be the pivot rows of A, not the RREF. So we can see that the row space is a subspace of Rn, so is the column space. Dimension is R, and column space also has a dimension R. The null space is of dimension n minus R, which is the nullity. And the left null space also has the same nullity. The left nullity is the same as the nullity. That's because it's a square matrix. M is equal to n. Now, if you look at a full column rank matrix, now you have 4 rows. So then you have an identity matrix near the top, then 0 rows below. Then what's the rank of this matrix? It is 3 pivots. It's full column rank, 3 columns, all of them are linearly independent. Rank is 3. What's the column space? Linear combinations of the columns. So that would be a subspace of R4 because each column has 4 elements. And the dimension of the column space is the rank, which is 3. Does AX equal to B have solutions? Only if the B that you've started with is a member of the column space of A. So here things begin to get more interesting. It could have 0 solutions when B is not a member of the column space, which means there will be a 0 row here, which might turn out to be non-zero on the augmented side. So that's when you have inconsistency and 0 solution. Or if that actually turns out to be 0 here, then that will have a unique solution, but never infinity of solutions. What's the row space, which is the column space of A transpose? As you can see, all columns have pivots. So just take the 3 pivot rows, and that is the identity matrix. So the row space is all of R3 because each row has 3 elements. So all full column rank matrices will row reduce to this kind of matrix here, identity matrix and 0 rows. Identity matrix and 0 rows. This would be the number of columns, the size of the identity matrix. Rest, the left nullity, will be the number of 0 rows. So if you look at a full rank tall matrix, you have a shape like that, identity standing on top with 0 rows padding below. The basis for the row space would be at the identity matrix. Basis for the column space will be all columns of A because all columns are linearly independent. All of them have pivots. So the row space is all of Rn. The column space is a subspace of Rm with dimension n because that is the rank. Null space is a trivial null space, the set of 0 vector because the row space has taken up everything. The left null space has m minus r as the dimension. Remember, m is greater than n, so there are some free variables in A transpose, and that will give you the basis vectors for the left null space. If it becomes rank deficient, it becomes even more complicated. The top part now is not going to be just an identity matrix, but it's identity matrix with shuffled in free variables. This you have seen before. The thing to notice is that the row space is a subspace of Rn, the input side, in green. Column space is a subspace of Rm, output side, in red. Purple null space is a subspace of Rn. Blue left null space also is a subspace of a bigger space, Rm this time. The nullity is n minus r. The left nullity is m minus r. Wide matrices. I have RREF of this wide guy here, computed by Sage Math or something. What's the rank? It is a full row rank, so 3. All rows are linearly independent, so the rank is 3, and that is the same as the number of rows. What is the column space? Column space is all of R3, so the basis is, a good basis is IM, or you could take the 3 pivot rows here, that is column equivalent to the identity matrix. Does it have solutions? Always, because you have one free variable which will give you an infinity of solutions, and equations can never be inconsistent because you don't have a 0 row here. Always infinity of solution. What's the row space? Row space is a subspace of R4 because you have 4 elements in each one of those row vectors, and the dimension is rank, which is 3. All full row rank matrices will row reduce to some identity matrix with free variables, and they may not be cleanly separated like this. They may be shuffled in. The free variable columns may not come near the end. It may be somewhere in between, which is what this symbol means. Now let's go through this once more. If it is full rank, m by n with m being less than n, fewer rows than columns, wide, the basis for the row space would be the pivot rows of A, or its RREF or REF. The column space will have a basis, which would be the pivot rows of A. The row space is a subspace of Rn. Dimension is M. Because it's full rank, that means all rows have a pivot, that is the maximum rank. Column space is all of Rm, so the pivot columns will give a basis, and so will an identity matrix. Since the column space has eaten up all of the output space, the left null space has got only the 0 vector in it. If it is rank deficient, then it becomes much more interesting, complicated. So it will have an identity matrix shuffled in with free variables. The size of the identity matrix is the same as a rank, which is less than m and n. It is wide, so m is already less than n, and rank is less than the number of rows. So there are some rows with no pivots, which will get pushed down to the bottom part of its REF and RREF. Basis for the row space, pivot rows of A or its REF, RREF, etc. Basis for the column space will be pivot columns of A. This time it's all subspaces, so you have to be careful to take the pivot rows and pivot columns. So row space is a subspace of the input space Rn in green. Dimension is R. Column space is a subspace of the output space Rm. Dimension is again R. The rest of the dimensions will end up in the null space n minus R on the input side, m minus R on the output side. Null space and the left null space in purple and blue respectively. Now let's take the most general case. M by n matrix, any shape. Rank is R, which is less than the possible maximum rank, so it's rank deficient. So its RREF is going to be an identity matrix of size R shuffled in with the rest of the free variables and with m minus R rows that have become 0 rows. So to say this once more, you must be getting bored, right? The basis for the row space would be the pivot rows of A or its RREF. Basis for the column space will be the pivot columns of A, and that's what I've written down here. One last time. Row space in green is a subspace of the input space Rn. Dimension is R. Column space in red is a subspace of the output space Rm. Dimension is R, the rank. The null space in purple is a subspace of Rn, the input side. Dimension is whatever the row space has left for you, which is n, the number of columns, minus the rank nullity theorem there. And the blue left null space has the rank nullity theorem of A transpose, where the dimension is m, the number of rows this time, minus the rank R. Voila. Now I have some things that I would like you to work through. Very simple examples. So a skinny matrix, yes, one column. What's its rank? It's 1. Is it full column or row rank? It's a full column rank because only one column. What's its row space? What's its row space? It is R1, which is just R, it's just number. Now look at A transpose, let's call it B, and can you answer the same questions there for B? What's its rank? What's its row space, column space, etc. Now go one step further, compute A transpose A, that turns out to be a scalar. What's the rank of A transpose A? It is 1, it is full rank. What about A transpose? That is going to be a 3 by 3 matrix. What's the rank of A transpose? That is again 1. So please verify that the null space of B is the same as the null space of B transpose B. And can you also verify that the rank of A and the rank of A transpose A and rank of A transpose, they're all the same? One more. 2 columns this time. What's the rank? It's 2. Full column rank or full row rank? Column rank. The row space is all of R2. What about B or A transpose? All answer the same questions there. What is A transpose A? That would be a 2 by 2 matrix. What's the rank? That is going to be a full rank. What about A transpose? That's a 3 by 3 matrix again. What's its rank? It is 2. And please verify that the null space of B is the same as the null space of B transpose B, and verify this also. I'm talking about tall matrices, full column rank tall matrices, because in computer science, the data matrices tend to be tall matrices and they tend to be full column rank too because they are real measurements. Now, there is one last slide. We saw that the row space, column space, left null space, etc. They had some strange names like kernel, image, etc. Let me give you my theory about where those names are coming from. So let's consider a function which maps a value in R to another value in R, which is the square root of x. And let's compare that with our transformation, which is A, which takes Rn and gives you a value in Rm. So here it is R to R, here it is Rn to Rm. So the domain for a function is a space of all possible x, that is just R in this case. Similarly, it's the input space here, Rn. Codomain is a space of the function output is going to be a real number 2, so that is R as well. Similarly, codomain is Rm in this case. Range is actually all possible values of f of x. There are some values in R that f of x cannot take. For instance, it cannot be negative because square root written this way is defined to be the positive square root. So f of x has to be greater than 0, and that is the range. So that is like the column space, and it's also the image because fx takes x and gives you its image. So that's the column space. Coimage is all possible x's that you can actually apply to this function. That is again x greater than 0, because if it is negative, then it's square root of a negative number, which is too scary to think about. So that is the coimage, and that is equivalent to row space. I am stretching my analogy a little bit here when it comes to the row space. Kernel in the case of a function is the value of x such that the value of the function is 0, which is just one number 0 here. That is the null space. Cokernel is the part of the output space that you cannot access by the action of this function. Fx can never be less than 0 because it's square root of x, positive square root, and that is a cokernel. So nothing gets there, but it is not empty. Even in my toy example, fx is less than 0 is the part that you cannot get to, but that's not empty. That is actually the number line, all real numbers that are less than 0. So that brings us to the end of this 4 fundamental spaces. And next week, we will actually move on to projection and a real machine learning algorithm, which is that comes out of projection and linear algebra in a very beautiful, elegant, surprising fashion. So stay tuned.